Okay. All right, so thanks again for coming along. This second workshop for MUX/ARPS online series for this semester. Thanks so much for coming. This one's a new workshop that I've developed over the last couple of weeks, and given sort of the remote nature of subjects this semester, we thought it'd be good to offer some Simulink and get up to speed on what it is and how to use it, and basically yeah, the sort of main uses you'll encounter it in the sort of subjects you'll be taking. So yeah, if there's anyone, I'd just like to get an idea of what sort of level people are coming into this in terms of MATLAB/Simulink use. You should be somewhat familiar with MATLAB at least, and yeah, if you have absolutely no experience with Simulink at all, that's fine. Or if you've used it, you might learn something new as well, or just after a refresher should be able to cover all those cases. And yeah, but we'll be sort of going from the very top. So yeah, certainly if you haven't done any Simulink at all before, then it'll be completely fine. So you'll find the slides in the text channel if you haven't seen it, in the Remote Hardware Labs text channel. Grab the slides and you can have a look at them yourself, and because as I go, sometimes the slides will be moving off the screen that I'm sharing. Feel free to yell out if you've got any questions in the voice chat, or I'll be keeping an eye on that text channel as well. So post up anything that comes along, that's not a problem. Any issues that you're having, anything that you have questions about, just let me know. Yell out, it's not a problem. Okay, so Simulink, it's a MATLAB product. It's an add-on for MATLAB. So if you haven't done already, get MATLAB fired up, get that ready to go, and yeah, it integrates quite nicely. Slightly different way we use it, but they do tie in together for sure. And yeah, the Simulink is basically simulating and designing dynamic systems. So dynamic systems being a system that changes with time. And one of the, for better or worse, Simulink is designed and realized using block diagrams, which can be quite detailed, or they can also sort of show quite abstract systems as well, with the idea of block diagrams. So quite used quite a lot in all types of engineering, in describing how signals move between systems and how systems are linked and things like that. So you will be using block diagrams there, and they're built particularly using the ground up, which is what we'll be doing, using primitive blocks. So like your fundamental mathematical building blocks and tools, but also people spend a lot of time designing higher level, more complex systems as blocks that we also can have access to as well. We won't be doing too much of that today, but it's all about what blocks do and how they change a signal, and how they integrate with part of the system. So yeah, all about blocks and block diagrams, and particularly, I guess there's this thing that if you look up what Simulink is, they talk about this thing called model-based design, and that's it's this thing in engineering where it's used in the design process to essentially use a computer to model a physical situation, tweak it, change it, find it, break it, find out what's going on with it, and then take it back into the real world, and hopefully with some benefits like minimizing the risk, reducing cost, and you might be able to get it quicker. You can see what's happening with the system sort of immediately, or at least the time it takes for you to run a simulation, rather than having to build the whole thing and then implementing that and finding out that it doesn't work because you mistyped in a parameter or something like that and had 1,000 parts made or something. So model-based design, yeah, quite, particularly since the starting of computing and engineering, the idea of simulating your system first is widely used. And yeah, say hi to Knuckles. This is my cat Knuckles. He's not particularly enjoying the move at the moment. He's still getting used to the place, but sleeping under the covers most of the day. He's made an appearance now. It must be close to his dinner time. Okay. So yeah, as we said, it's used for describing any sort of dynamical system. So things like mechanical systems, electrical systems, thermodynamical systems, population dynamics, anything that can be described mathematically, so mathematical building blocks, and anything that evolves in time as well. It's sort of, time domain is quite sort of intrinsically linked to frequency domain as well, but we should be aware that we're describing a dynamical system at its core. We can still get frequency information about it, but we're describing it in the time domain. So a dynamic system. Specific uses that you might come across, things like rigid body dynamics, motor control, antenna modeling, digital systems I've seen, things like hydraulic systems, so anything that's going to be changing with time we want to be using Simulink for. And a quick overview of systems in general, like quite broad overview, sort of the core signals and systems in about 2 slides. So a system in general is going to convert one or more input signals to an output signal, one or more of them. And in Simulink, we think about a system as a block, this abstract idea of a block. So they map input to an output in different ways, sometimes simple ways, and sometimes they can be more complicated as well. So here's a block that has one input, so input on the left-hand side with an arrow going into it, and one output on the right-hand side with the arrow coming out of it. So another system, 2 inputs and 1 output, 2 inputs, 2 outputs. And for all intents and purposes, we don't necessarily need to know exactly what's happening in this system. All we need to know is what signals do we feed into it, and then the system does its thing, the block does its thing, and then it's going to spit out one or more signals out the other side that have the imprint of the system on it, whatever it does to that system. And we'll see lots of different types there. But fundamentally, it could be a simple system could be like an additive system where 2 signals get added together. So that might be something like this system be one signal coming in, another signal coming in, and then the sum of those 2 signals coming out the other side. So it can be simple or all the way up to a really complicated system, which could be like a car or something like that, where you've got your accelerator input, you've got your steering wheel input, and what comes out the other side, or it might be your position or velocity or something like that. And the exact dynamics of that system could be very, very complicated. So yeah, simple or complicated, depending on sort of how zoomed in you are to the particular system there. Large systems can have many subsystems, and as we talked about at the lowest level, that system is going to be able to be broken down into the primitive mathematical and logical building blocks. So the super system, this big system, has 1 input and 1 output, but if we have a look inside of that big system, we've got 3 different subsystems, and they're all interconnected and may have feedback loops and things like that. Just depends on how zoomed in we might be and exactly what these systems are doing. So that's sort of at the abstract level. We'll quickly have an overview of some blocks that are available in Simulink before we actually get into Simulink, because I think it's good to, I guess, know what's available, and then we'll see the specific implementation in Simulink there. So, quick overview. Here's some math functions as blocks. Sums, products, absolute values, gains, so multiplication, it's another type of sort of like a product in a way. Cosine, sine, exponentials, logarithms, common math functions. And yeah, you can think about how they're going to act with the inputs and the outputs there. Time domain operations. So we've got integration, so we can integrate a time domain signal. If you've done Laplace transforms, that'll shed some light on why this has a 1 on S symbol to sort of identify it as an integrator. So that's got to do with Laplace transforms, second order integration, so we can integrate it twice, and we can see that this will give us the the first derivative, and then we integrate that up again. That signal coming out of there will be the doubly integrated signal. We can take derivatives of an input signal. We can use like a frequency domain transfer function or class domain transfer function. We can do time domain convolutions. We can do delays. It's a bunch of time domain operations. Different types of logics. So logical ands, nands, nots, ors, nors, and exclusive ors. They're all available there for our logical blocks as well. And those symbols should be familiar if you've done any sort of Boolean logic or circuit logic. And ways to route and manipulate signals as well. So switches, conditional switches, mux, which is a multiplexer, which will combine basically one or more signals into a single one, or two or more signals into one single one. Demuxes, which does the opposite, or buses, which are sort of similar to muxes. And sources, signals need to start somewhere, so we've got a bunch of signal sources here. We'll explore a lot of these. A clock, which basically tells you what time it is in the simulation time. Constant blocks, step functions, sines, ramps, pulses, white noise, chirps, and we can also get signals from our base MATLAB workspace. So if we define a signal in the MATLAB workspace, we can pull that into Simulink with this from workspace block as well, so that can be useful. Sinks, so places where signals can go, a display, a scope, which is probably the most used one, to workspace, which is similar as well, and an XY plot, which can be handy depending on exactly what you're simulating. Alrighty, let's jump into some Simulink, actually doing some things. So to start Simulink, we open MATLAB, and then at the command line we type Simulink and press enter, and we'll see Simulink start up. So let's do that now. Follow along, Simulink. I type that in and I get this window, at least on my version. It might look slightly different on your version of MATLAB. Mine's 2019B. You get this, and we're just going to start a blank model. So find a way to create that blank model. And you should get a window that looks something like this. So we've done all that, created our blank model. This is mostly where you'll start when you're working in Simulink. You'll be creating a blank model and then dropping things in there. Occasionally you might be given a model to work with or given a block to work with, which you can import and things like that. So the main workspace, this big white area in the middle, some commonly used tools down the left-hand side of our workspace. We've also got the run button, which is a big one. You'll be using run a lot to run your Simulink simulations. You should be able to expand a model browser, which shows you all the different things that are in your model. Depending on how complicated your model is, that might be useful. The stop time of your simulations up here, it's all grayed out because there's nothing in there at the moment. And then the library browser as well is pretty common. So if you click on the library browser, you'll see the basically all the blocks that we've got access to come up. So if you open up that library browser, you can see there's a lot of different blocks there to be able to play around with, and you'll find some of the ones that we've seen before. You might see some different ones depending on what toolboxes you have installed. So some toolboxes provide Simulink blocks as well specifically. So most of the base level stuff will be easy as to work with. So that's the basic MATLAB, the basic Simulink window that we look at. In general terms, what Simulink is doing under the hood, it takes our system at time t, and then it evolves it to the state of the system at time t plus delta t. And it's just going to keep doing this, updating that simulation based on whatever's happening in our blocks. It's going to do that, sort of keep doing that iteratively until the simulation gets stopped. So it either reaches the stop time or we stop the simulation manually. Delta t is known as the step size. And we can change this. We can change all the different ways that Simulink works sort of under the hood. But most of the time, the default's going to work pretty well for us. Particularly if you're doing continuous versus discrete simulations, you might need to play around with that. We're going to mostly be doing continuous simulations today, which is just the default setup. But I think I show us how to change it. Yeah, if we want to get to the solver settings, we can go into the modeling, model settings, and then that's going to bring up the window here. We can see what the solver is being used, particularly variable step. So that means the delta t time in this time evolution. The delta t, a variable step size, means that delta t changes and gets bigger or smaller depending on what Simulink thinks is the best way to sort of step us forward in time. So if you're working at the nanosecond scale, you might need a very small time step. If you're working at the months-long time step for doing like orbital dynamics or populations or something, stepping every nanosecond isn't going to be great. So we want to make sure we've got control over that. The default is pretty good, but we can do variable step or fixed step, which is what you would do if you were doing a discrete simulation. Every step through is the same each time, and yeah, you can change the different type of solvers here. Discrete, variable step is pretty useful. ODE 4.5 is the usual solver that will get used. It's a very versatile, very quite good solver. The ODE 4.5, it solves a dynamic system based on differential equations, and that's pretty much what's happening. But we'll just leave it at the default for now, for what we're going to be doing. Okay, so we're just going to drop in a few blocks here to get us familiar with the general work. So follow along, jump ahead if you need to, depending on how much Simulink you've done before. This could be review or just getting familiar, but I'll run through a little bit. We'll add a clock block, and we'll connect it up to a scope first of all and see what's happening. If you need to quickly add a block, you can just double click on the workspace and it brings up a little search tab, and then you can type in the name of the block that you're looking for. So we double click, type in clock, and sometimes it can be a bit confusing. Simulink's going to give you a bunch of different stuff that sort of looks the same, and they all come from different libraries, different toolboxes. I haven't really gotten myself in trouble by choosing sort of random ones. Usually the first one's good, but in this case, Simulink/sources is the one that we want, that clock. And depending on, Simulink extras / flip-flops, this clock will be like a timing clock used in a discrete sort of digital system. But yeah, just a continuous clock. Looks like this in the workspace. And we're going to connect that up to a scope. So double click, type in scope, and that's a Simulink/sync. That one there, it looks like that. And you can see it's sort of giving us a hint that we can join those up with a signal connection. You can either click on the arrow and sort of drag to your, drag from your source over to your sync, or you can sort of use Simulink's auto suggestions and just click and it'll route it anyway. So this is all we want at the moment. There's this button here on the left-hand toolbox is pretty handy as well. It's going to blow it up to the sort of fill your workspace up with the blocks that you've got, and you can also use the scroll wheel to zoom in and out. So we just have a clock connected to a sync, being a scope here. Anyone want to have any clues what's going to happen if we connect view what's happening on the clock and we run our system, run our simulation? We hit run. Doesn't look like anything's really happening. I think I might need to, let's see, here it is, and probably a good idea to save your Simulink model first, so I might just quickly do that. Just to make sure I'm going to call this Simulink Workshop. Yep, Workshop. Sweet. So we clock connected to a scope. It's all saved. We run the simulation using the big run button, and we double click on the scope to bring up its output, which just looks like a graph. And we can see basically the input to the scope plotted against time. So they don't do a great job of sort of showing labeling their axes. So basically a scope's x-axis is the simulation time. So you can see it runs from 0 to 10. And the y-axis is the signal that's coming into the scope. So in this case, it is t. So t is coming in. The clock just outputs t. Every, and that looks like a straight line, which hopefully makes sense. At time t equals 10 of the simulation, the time of the simulation is 10. Pretty straightforward. So that hopefully does what we expect. Let's add some common maths functions and connect them up as well. We can see we can drop in some sums and gains, and we'll see what happens when we add a bus in as well. So if you're following along, just go nuts. Drop in some of those common maths functions that we saw back on one of the first slides where we showed the blocks. So we've got sums, products, absolute values, gains, cosine, sines, all of that stuff. We'll just drop some of those in. And I'll do it here, but feel free to jump ahead. So let's add in a sine. Why not? So looks like this. Now if you want to grab, so sine is going to take the sine of whatever the input is, and on the output it's going to give the sine of that value. So if I connect it up to our clock signal, it's going to give us sine of t. If I want to connect up to this connection here, I can hold down Control on the keyboard, and that's going to allow you to drag off a new point off that signal. So we drag Control click off the clock signal and drop it into the input to this sine block. And then the output, we're just going to connect that up to the scope as well. Something like that. So when I run my simulation now, I should be seeing one of my plots being t, so that's that signal there, and another one of my functions being plotted being sine of t, plotted as well. So I bring up my scope, and yeah, we can see that now going as well. Sine of t in blue, and t coming in the yellow there, the first one there. So we'll just follow doing that. I'm going to do exponential. We'll drop in a gain as well. So gain is just a simple multiplier. If I double click on the gain, so if you double click on a block, it's going to bring up all the block properties that you can change. So if gain of 1 is just going to be 1 times whatever's coming into it. So 1 times a signal doesn't do much, so let's make that, it's going to be e to the power or something, so let's sort of squash that down a bit. Let's change that to a gain of 0.1 maybe. So it's going to be 0.1 times whatever's coming into it. Click OK, and we can see the 0.1 comes up in there. I'm going to drag another point off my clock signal, drop that in there, and then another input into my scope. Can drag these blocks around, get it looking a bit nicer. Okay, so in my scope plot, I should see t, sine of t, and then e to the power of t. So u is just a generic input variable that we see here. So inputting it is t. So e to the power of t times 0.1 into the third value. So I can bring up my scope. And then there's also a little run button on my scope here that can be useful as well. You don't always need to come back to this big run button here. There's a little run button on the scope if you want to see that, and you can just hit that and it's going to run as well. And you can sort of see it going on, and you can see, yeah, e to the power of t blows out pretty quickly. So maybe if we want to play around with our simulation time, maybe we set it down to 3 or something like that, instead of going all the way through to 10. Run our simulation. Yep, so there we can sort of see something that's happening a little bit easier. Right. I think one more thing I wanted to touch on there. Anyone come up with any other blocks that they added? Find anything fun? You can do sums. Maybe I'll do a sum here as well. That's a common one. I'm just going to delete these ones, and I'll show you also using a mux to sort of might simplify some routing. Whoops, go away. let's add a sum, because sums, you might need to play around with them a little bit. If you double click on the sum block, it's got this, it gives a good description here about what's happening, but we can change the operator, whether it's a sum or a minus, like an addition or subtraction there. So if I wanted to do 3 signals, I wanted to go like one signal plus another signal, but then minus the last one, I could go plus, plus, minus. Just go apply. So you can see it goes from sort of the top counterclockwise around plus, plus, minus, and then the output is going to be this signal plus this signal minus this signal. You can add in that vertical bar to be a spacer. So it'll go plus, nothing, plus, minus, and the spacer just sort of can arrange your signals, arrange where the inputs are coming in a slightly different way, depending on how neat and tidy you want your blocks to look. But that would be exactly the same as, plus, plus, minus. It just looks slightly different. So let's do, why don't we go, control click to get that new signal coming on. Let's go t plus sine of t minus minus 0.1 e to the t, and we'll feed that into our, let's go to our second scope input. Oh, actually, no, I said I was going to do a mux, didn't I? Delete. You can see sometimes it can be a bit finicky on where you click. So I'm just going to right click, and on the signals and ports, when I click on a scope, number of input ports, it sort of automatically goes up when you're adding new signals to it, but you can sort of, that can be a bit hard to delete. So you can change that back to 1. So that's right clicking on a scope, signals and ports, and then number of input ports. And yeah, you can get a lot of options when you right click onto a block. So before I feed into my scope, I'm just going to add in a multiplexer, and that's going to combine a few signals for me. So first signal, maybe my second signal, I want to just have a look at the 0.1 e to the t component. Maybe another one that I want to have a look at is the t component. You can sort of connect that up to the mux, and then you can just connect one single output from the mux into the scope there, and that can sometimes simplify your routing a bit. And if I run my simulation now, double click on the scope, I've got all my signals there, and then essentially what the mux has done has taken care of some of that routing for us. You can get a legend up by going view and then legend. And the legend can be helpful sometimes. Sometimes it's completely useless because the default legend name is the name of the block. So you can name blocks. For example, clock is relatively descriptive by itself, but maybe we can name our block T. So that was just done by clicking, and there is more options up the top when you sort of hover or click. There's those 3 dots. You can do different things. So hide block name and show block name if your name is missing. So I'm going to call that one T. This one I'm going to call sine of T. And then if we have a look at our scope, see that last one is just called gain. So that signal that's being fed into it is being named after this gain block. So you want to be descriptive with your names. So the name of this signal, depending on what we're doing, I'm going to, this one is going to be 0.1 exp t, and that can help when we're looking at our scope. If I run that again, it should refresh everything. You can see my legend is now giving me something a little bit more useful. In that I know that the yellow one is T because that's the name of my clock block. Oh, that's right, I put the sum here. So depending on, you can name your sum block to something more descriptive if we were doing, if it was a mathematical formula. This would be t plus sine t minus 0.1 exp t. You know, naming it a big mathematical formula probably isn't the best way to go in general, but because we're just doing a simple example, that can be useful. So there it is. There's my mathematical functions t plus sine of t minus 0.1 in exp t, and 0.1 e to the power of t. All right, any questions from that, guys? So that should hopefully get a bit of a flavor for simple stuff. We might quickly do some derivatives and integrals, just because they are used quite a lot. So any one of your signals, we'll just drop in a derivative. Let's take the derivative of this this sum function, because that was sort of interesting. Drop that in. You can see very quickly, you know, as you're just dropping things in randomly, your block diagram and interconnections can be pretty confusing. You know, imagine if you were submitting this for marking or something like that. It's not great. You want to make sure it's nice and tidy as much as possible. You can have some luck with highlighting everything, right-clicking, and then there's arrange. So you can get all these different arrange options for helping you to align your blocks. There should be arrange automatically, and you may have some luck with that. Sometimes it's not great, but you can sort of tweak it a little bit by, you know, dragging your blocks around specifically to where you want them to go. So arrange automatically can be a help sometimes, depending on what you're doing. Sometimes it's completely useless as well. So we'll take the derivative of this interesting summing signal, and we'll feed that into our mux. Drop that in at number 4, and then we'll take an integral as well by dropping in an integrator. And we'll do it from that interesting sum signal as well. So control click is going to allow me to take off of that signal, feed it into the integrator, and then put that in. And they should be named relatively okay for the for these purposes anyway. So bring up our scope, hit run, and there's all our different interesting signals that we can see here. Derivative, integrator. What do we need when we're integrating a signal? Constant of integration, right? The initial value of our integration. So if we double click on the integrator block, we see the probably the main thing that you'll be changing a lot is this initial condition, and that's the initial value. So default is 0, which is quite useful. Most of the time we want to be starting at 0, but sometimes you will need to specify an initial condition for your integrator. So if our initial condition was, you know, 5 or something like that, just type that in, hit OK. Now let's have a look at how the signal changes. So integrator is the purple one. We can see the initial value. Now, you've got all your zoom controls if you need to. Initial value of purple was 0. Initial value of our integrator was 0. And then if we run that again, I've just changed the initial value of my integrator. Purple has now gone up to 5 to basically, yeah, follow the initial value that we set there. So that can be very useful depending on what you're doing. Sweet. So parameters, definitely that initial value of the integrator we want to be careful of. And in general, always work from left to right, input to output. The way that blocks are laid out with the input on the left by default and the output of the right should clue you into that. To work from input on the left-hand side to output on the right-hand side. And as your systems get bigger and as you want to quickly jump to different parts of your system, following that convention can be very, very useful. You can, if you need to, if you really need to, you can rotate a block. So let's say we wanted to rotate this gain block. You right click on it, rotate and flip. You can rotate it clockwise, to sort of make your block diagram look nice and neat. Should be the main goal. So yeah, if for some reason we want it going that way from right to left, that can happen as well by rotating a block. But most of the time, you just want to keep things flowing from left to right. Now I've got this there, let's just go Control-Shift-A, see if auto-arrange does anything. See, it doesn't really do anything useful for me at the moment. Things that's in the best layout as possible. Okay. If you're brave, have a try of the to Workspace command. I might quickly show you that. Why not? To Workspace. For example, if you want to save everything, you can save a specific signal just by grabbing that signal, routing it in. But perhaps in this case, what I might do is route in my my muxed signal there, so we can have a look at it. And you change the variable name, so the default sim out for that one will be okay for the moment because I don't have much else going on. But if it was something that we were working with, like it was the position or speed or something like that, we might give it a better name depending on what it is. I'll leave it as simout.now, and it's going to be. We'll see how that goes. So I'll run. And then what we need to do, we need to jump back to our MATLAB workspace, and we can see now that we've got a out variable here. It wasn't there before. We type in out. It's a structure. It's a MATLAB structure. Depending on how much MATLAB you've done, you may or may not be familiar with what a structure is, but it's basically holds all the different variables. So in this case, it's a Simulink structure specific. It's got some things. So simout was the variable name that we defined. The T out is the simulation time. So you can see there's 51 values in that. So there was 51 different time steps. We can have a look at that. Out, sim out. There's a time series, and then in that we've got different stuff. Out.simout will hold our variables. And again, it's another time series. But data is the one that actually holds the data. Out.simout.data is the way that we would access that, and there's our array, the base array, and that's we can see that each column is a different. Each column of this, because we're using a mux here, each column is one of these signals coming in. So the first column is going to be this one, the second column is going to be that one, third, fourth, and fifth, and so on. So all of that is available for us now as a basically as a MATLAB structure and as MATLAB arrays, which can be useful for different things. All right. Any questions? Anything unclear? I think we'll be moving on to the next little part of the workshop now, which is a sort of little bit more of an actual model, something a little bit more fun, I guess, and more of a real-world situation. So we'll jump straight in. We will have a little bit of a break. Hopefully we'll hit, I think we're on track to hit about 2 hours exactly, which is good. We'll have a bit of a break at about 6, but I'll just get us set up for this next one. So what we're going to do, we're going to use Simulink and we're going to solve a dynamic system. We're going to simulate the dynamics of a point mass, and it's only going to be moving in one direction. And just for purposes that will become a little bit clearer later on, let's call it a rocket, and we're going to imagine that rocket's moving up and moving down only in the y direction. So it gets launched from the ground, goes up, and then it just gets whatever happens under the dynamics of the system. So that's sort of the abstract idea of this exercise. Specifically, we need to know how the system evolves in time. So what governs how this system changes? What governs the dynamics of the system? What are the maths? What's the maths that underpins it? And that is, in this case, for dynamic motion, is Newton's second law. We're not traveling super duper quickly or near high gravitational fields, so we don't need general relativity, which is good. So Newton's second law will help us out here to keep this nice and simple. So if you've done a bit of physics or mechanics, F equals ma, or particularly the sum of all the forces in vector form in 3 dimensions equals the mass multiplied by the acceleration. For our one-dimensional case, we're going to express it like this. All the forces, the sum of all the forces acting in the y direction divided by the mass equals the acceleration in the y direction only, because we're doing 1D. So double dot is the displacement, the second derivative of the displacement, if you haven't seen that notation before. In terms of inputs and outputs, okay, in terms of input to the system and output of the system, the input is the forces, and the output could be one or more things. Typically, we'll like to be interested in maybe the position and the velocity of the system. So probably one input. You might think of the mass as an input. Not really. It's more of a constant. But yeah, certainly the forces that are acting and the outputs being the velocity and the position. So let's start a new blank model. We'll start from scratch. Starting a new model, I'll save that, and I'll call it rocket. Save, and yeah, Simulink is a .slx file there. So if you see .slx's, and there's some other stuff some other files that sort of come along with Simulink models, which you might see in your folders. But yeah, SLX is the main one that actually holds the model. So rocket.xls, I'll just close out this last one, we don't need that anymore. So a new blank model, I'll clear out my workspace just in case. Okay, so a blank rocket model that we're starting with. Okay, so we're going to use constant blocks to define the constants of our system, which should be pretty clear at the moment for this simple case. We're only going to think about the force of gravity to start with. So the only force acting on our rocket is the force of gravity. And that's a constant. It's going to be minus 9.8 meters, oops, typo there, meters per second. I knew there was a typo in here somewhere. I forgot where it was, but I've just found it. 9.8 meters per second squared. With the mass of the rocket, we're just going to choose something arbitrary, 2.4 kilos. It's not a huge huge rocket. It's just maybe like a little model rocket or something like that. Mass being 2.4 kilos. So we're going to use constant blocks. Equally, we could set them up as workspace variables and reference them completely. We'll start with constant blocks for now, and we'll change them a bit later on, I think. So double-clicking, constant is a source, constant value, first one minus 9.8 for force of gravity or acceleration due to gravity, and another constant block is going to be, what did I say, 2.4 for that one. So two constant blocks, we'll name them G and M. Okay, so keeping nice naming here so we know what's going on. G and M, two constant blocks there. Okay. We're going to feed relevant signals into a summing block, because what forces act on our rocket in the first case? The only force that we're going to have to deal with is the force due to gravity. So the sum block isn't going to do too much, but eventually it's going to help us sum all the different forces. So we need to add a summing block. And for now, I just want there to be one signal there, so the sum block isn't actually going to be doing too much. Okay, so what is the force of gravity that acts on the rocket? It is, if we remember force due to gravity, F equals m times g. Okay, so one of the forces in terms of Newton is F equals m times g. So we need something to multiply those two blocks together. We'll use a multiply block because we want to combine, we don't want a gain block necessarily, sorry, a product block to multiply m and g together. So m times g is going to be the force due to gravity. So we might name this Fg for force due to gravity. And that's going to go into our summing block. So this sum block represents all my forces. Okay, so we're starting to get our model set up here in one of the forces being the force due to gravity. It's minus 9.8 times 2.4 meters per second squared. Newton, sorry, for the force. So F equals m times g. Okay, how do we relate that back to our dynamic system? Well, Newton's laws, right? So the acceleration equals the sum of all the forces. So in terms of our equation here, the sum of all the forces is going to be this block here, our forces block. So that's a sigma Fy. At the moment, we've only got one. And then we need to divide this by m. So if I take this output of all my forces and I divide that through by m, product, so one of them is the output of my forces. If I have a look into here, actually let's not use the product because I need to do divide. Divide there. So just double click on the block to get the parameters. If you just put one multiply, you can read, one divide symbol. If you read the instructions, you can do some sort of more complicated stuff than just straight up multiplication and division. We'll just use divide there. So that should be, oh no, sorry. We need to set it up as star and then slash for multiply and divide. So there's going to be one signal for the numerator and then a second signal for the denominator. Sorry if I had read that properly. So star and then slash there will get us what we want. So sum all the forces is our numerator and the denominator is our mass. So we need to grab another signal off our mass block and divide that through like that. So when we've done that, what does this signal coming out of that represent now? It is our, if we look at our equation, sum of all forces divided by m, that's what we got here, and that is equal to acceleration. So accel. So if we want to look at the acceleration, we can just have a look at this signal here. Will give us the acceleration of our rocket based on what forces are acting on it. Right, so we're going to integrate. How do we get, maybe this is all we want to look at. If we only want to look at the acceleration, we could just deal with this, change our forces around, look at this on a scope, and that could be it. But we want to get some more useful information. We're going to have a look at the velocity and the position. So if you have a look at integrators, there's a single integrator or there's a second order integrator as well. You can have a read on what the sort of pros and cons of using both of those are. We're going to use a second order integrator in this case, just because it does generally work better for problems like these. If you know you're dealing with acceleration, you want to get up to, you know, if you want to have access to velocity and position, probably a second order integrator is the easiest way to go. So we'll drop that in, and yes, we do want to feed in the acceleration into our second order integrator. And certainly dx will be the output of the velocity, and the position here will be x. So that's pretty much what we want. And if we have a look on a scope, we'll drop in an x, and we'll drop in our dx, and we might also drop in the acceleration as well, just so we can have a look at all those on the one scope. So we should have position, velocity, and acceleration there. Okay, let's have a quick look and see what our system is looking like. Just quickly double check our initial conditions. For x in this double integration, so that's our, you know, it says x, but it's actually y because we're thinking about vertical movement. Our initial condition 0, we're going to get that to start from ground height, why not? And we're going to get it to start with initial velocity as well, so 0 in that one as well. Okay, double click on our scope, run the simulation, and we should hopefully see what we expect to see from our simple system, right? It's going to get more complicated and interesting, I promise, but should be pretty straightforward. We'll just bring up our legend, acceleration, and yeah, if you can decipher the default names that the second order integrator is giving us, we should be able to see the position in yellow, parabola, and a straight line for the velocity as well. We just verify acceleration for this one should be minus 9.8, which indeed it seems to be. And knowing our dynamics, the slope of the acceleration should be the slope of the velocity should be the acceleration, and so on. So that all works pretty well. Great. So pretty trivial starting point. Why wouldn't we do this analytically? We'll see in a second, because we're going to grow this into something that's impossible to solve by hand. But yeah, this should just be getting you familiar with Simulink, and we'll get a little bit complicated in a second. But before we move on, we'll take a 5-minute break, and yeah, we'll come back at probably just a little bit past 6:05. So thanks for joining so far. It does get a little bit more interesting, I promise. But yeah, for the benefit of those who haven't seen Simulink before, hopefully this is allow you to get a little bit more comfortable. So I'll see you guys back here in about 5 minutes or so. Cheers. Okie dokie, let's keep on trucking through this example. So we just got our second order integration going. The have access to acceleration, position, acceleration, velocity, and position. If you wanted to, you could also drop a scope into our forces, like such. Maybe a separate scope depending on the scale, and drag a signal up into that one. So that will be our forces, and then you can have multiple scopes going, and you can see what's going on there. So forces on this guy should just be a straight line, as we know, pretty standard. So where's my PDF? All right, let's get into the interesting stuff. We're going to add quadratic drag to the rocket. Now, this is in the realm of we don't want to be solving this by hand. So something like Simulink, yeah, for this is great. So we're going to add quadratic drag into it, which is has the form of this. So the force of drag is a constant, k times a being the cross-sectional area, multiplied by the square of the velocity. So square of the velocity here. And you can hopefully see, you know, having access to the velocity here as a signal, we would be able to use it to, yeah, essentially figure out what the quadratic drag force is. So, adding two new constant blocks for A and K, we're going to use a product block and create the drag force. We may need to, because we need to think about the direction that the drag acts in, whether it's up or down. So we can use the sign block to help us with that. Hopefully you figure it out by yourself. If not, I'll explain how it works, and then add that new force into the summing block, and that'll be the sum, the forces. Okay, so I'm going to add a constant. Oop, not that one. Constant for K. Let's just, we'll come up with something. Let's maybe go 3 and see how that works. I'm not trying to be super accurate. So this is K and another constant. Constant value can be something reasonably accurate for our little model rocket. So maybe our rocket has like a, you know, it's a circle and it's got like maybe a 4 centimeter radius or something like that. So we can type in a mathematical expression here, pi times radius, which is 0.04 squared. Okay, and that will work fine for our constant. A for area. Okay. Then we've got, for the other ones, we need to basically create this force of drag, so K times A. So we need a product block, multiply, not multiply, I always get those mixed up. Did it again. Serious? Product. And in this case, I'm going to flip it around to come backwards, because this is an example of like a feedback signal. So it's a signal that's coming back from one of our outputs back into the input. So it can often be useful to organize those sort of coming from right to left in terms of a feedback signal. So K times A, how many things do I need to multiply together? I need 1, 2, 3. I actually need 4, and we'll see why in a second. So 4 inputs to our product. The output of that is going to be our drag force, and that's going to be another addition. So 2 things coming into our forces now. So this product block is going to be called FD, so drag force. Okay, so drag force has K multiplied by A multiplied by, I need the square of the velocity. I'll just tidy these up a little bit. That one can face upwards. That one can face upwards too. I need the square of the velocity, so I add in a square function that's available. I find my velocity, grab that velocity signal, chuck it into my square, so this is going to be v squared. And then the final piece of the puzzle is the sign. So at the moment, squaring the velocity gives sort of, we lose all the information about whether the velocity is positive, so upwards, or negative, downwards. The drag force works in the opposite of the direction of motion. So when the velocity is positive, going upwards, we want the drag force to be acting downwards. When the velocity is downwards, we want the drag force to be acting upwards. So that's where this sine function comes in. Sine, okay. So sine, if the value going in is positive, sine is just 1. And if the value coming in is negative, sine is -1. So drag, we're going to use our velocity for that. And then we need to get another gain and just multiply that by -1, because when our velocity is positive, we want the overall the overall product to be negative. So that will, if we change this to -1, like so. So now when velocity is positive, we multiply that by -1, and that's going to be negative. So overall drag force is going to be negative, downwards. And when the velocity is negative, this is going to make sure our drag force is positive. So that should be all we need to do to get Simulink to simulate the very complicated, actually, problem of quadratic drag. Okay, and we've done that in all of 4 or 5 blocks, or something like that. Okay, let's have a look at what happens to our simulation now. Run that. Okay, so we can see it starts off as a parabola, but gets to be something that's not a parabola in the later stages. So you can tweak maybe the k value. Let's chuck this up to maybe 10, see what happens. Yeah, and we should see a change on, we should be able to see what, if the rocket has a terminal velocity. So that's this blue line here, right? The blue line before was linear. Now the blue line actually has a, it levels out. So I'll just zoom in around that blue line. See here, the blue line starts off linear, but then it tapers out and reaches a maximum value of a bit over -20 meters per second. So our rockets, we've just let it go from our ground position. So at the moment it's falling through the ground and reaching a terminal velocity of -20 meters per second there. So there's our quadratic drag force. If we wanted to have a look at the actual force that's happening, the drag force, here it is. Okay. Right. So we're going to add some power to our rocket now. So at the moment it's just falling through the air, which is pretty boring. We're going to give it some thrust power. We're going to find an appropriate source that's going to deliver a constant upwards force to the rocket for a certain amount of time before turning off. So that's like our rocket motor burning for a certain amount of time, and then it's going to turn off. Okay, so the signal that could be used for this one, looks like I don't have too many people joining me at the moment, but I'll keep going for the benefit of the recording. So lucky you if you're watching along at a later date. The signal that we might use for this one, we're going to use actually a pulse generator. Will be able to do this job for us. So it's sort of like a square wave, but we have a little bit more control over what the pulse generator does. So amplitude is going to be, it's basically what's the height of our square wave, or the height of this rocket. In this case, it's going to, it's the force in newtons that the rocket motor is going to be applying to our rocket. So that might be something like 50 newtons of force or something like that. The pulse width, the period is going to be, we're going to take it to be 10 seconds, and a pulse width of 5 seconds. Let's just leave that as a as the defaults, and phase delay, so when do we want it to turn on. We'll get that turning on from the start as well, so we can leave that. So there's our pulse generator, and we can just feed that straight into the our forces. Okay, so I'm just going to do another sum of forces, a plus there, like so. Okay, I'll just tidy this up a little bit. So drag force can come into the bottom, force of gravity in there, and then our thrust force can come in from the top. Name it thrust, so keep some nice a nice naming convention going on, and let's just have a look at what that thrust force is doing as well, and we'll feed it into that scope. That one there. So run our simulation, let's see what happens. Okay. So having a look at our forces first. So thrust, just turn on my legend. Thrust was this yellow. I'm not sure exactly why it's giving me circles around that. I don't really need circles. That's better. So thrust force we can see is 50 newtons. So here's our pulse, 50 newtons for 5% of that wave period. You can see it's just turned on at the end there, so I might adjust that for a longer time. Might put it up to 30 seconds or something. And yeah, you can see our forces acting there. They can get quite complicated. And here's what happens to our position and velocity and acceleration. So now our position graph, our first order, the first output of our integrator, we can see that is climbing up for 1 second until our thrust turns off. Well, sorry, it goes up. Our thrust turns off about here. This is this big discontinuity in the acceleration. We start off with a big positive acceleration, then we drop into negative acceleration, but it keeps going up because it's got some velocity. And then, yeah, it'll start to fall back down to the ground. You can see how long is it in the air? A bit over 1.5 seconds. So let's just change this up to about a 30-second period. So that's going to be a 5%, that's going to be a 6-second burn. And let's change that to something a little bit more interesting for us. Let's make it like 100 newtons. And run that again, see what our rocket does. Sweet. Okay, so we can see our rocket is getting to a maximum height of a bit under 60 meters. Our rocket is we can see that our quadratic drag is starting to have an effect. Our velocity from our constant thrust force isn't going up quite linearly, but our quadratic drag is sort of taking it in, and we can see, yeah, we do get to we reach this terminal velocity on the fall as well. If we accelerate it upwards for long enough, we might hit a terminal velocity vertically as well, but it's mostly here that we see it in that falling period after the rocket turns off. So rocket burns, goes up, turns off, keeps going up, gets to the height, and then calms back down. Sweet. We'll conceptualize and implement a parachute system. Again, this is a tricky thing, but we can do it pretty easily in Simulink, and with a reasonable deployment logic. And since there's no one here to answer my questions, I'll tell you the idea of it. But essentially, we want to monitor the velocity of our rocket and monitor the position so that we can get a parachute turning on when our rocket is falling back down to the ground, and it becomes and it reaches somewhere close to the ground as well. So we'll come up with that and implement some deployment logic. So we want to have access to the velocity, the position, and parachute conceptually doesn't change much except for the effective cross-sectional area of our drag force, right? So when our rocket's going up, it's got a small circular cross-section. It goes up, it comes back down, it falls, and then when our parachute deploys, all of a sudden we've got this big surface area. So if we play around with this cross-sectional area of our rocket to take sort of into account the parachute, we're going to be in a good spot. So we've actually got all the different knobs that we need to turn to have this parachute system going for us. So there's the final one if you want to have a look, but I'll quickly work through it as well, just to explain some stuff. So we start getting into some logic here. So first we want to monitor, are we close to the ground at all? And how do we do that? We monitor the position of our rocket. So we can use a, I think it's an if. No, not that one. I forget what the block is. I think there's a less than. Yeah, okay, so less than. So less than block. If, so we might do a constant. I wonder what that one there is. Compare. That's the one that I want. Compare to constant. So that sort of does my less than all in one, except I can just hard code in. So I want to use operator less than or equal to, that's fine. If close to ground, let's say we want it to deploy within like, I don't know, 15 meters of the ground or something like that. And it's going to be Boolean output, that's fine. And if what is less than 15, if our position is less than 15, so I'd take my position into there. We also need to monitor the velocity, because you imagine if I just monitored the position, it's less than 15 meters above the ground in the launch stage as well, not just when it's falling back. So if we monitor whether the velocity is downwards as well, that can be useful. So less than, so we'll get another compare to constant block. Feed that back as well, so I'll rotate that. And we're just going to compare that to 0. And it'll tell us whether it's falling or going down, and that will be enough to trigger our parachute system. So grab the velocity signal here. So if my velocity is less than or equal to 0, or my height is less than 15 meters, we want both of these things to be true. So we're going to feed that into a logical AND block. So both of these things to be true, that and that. And then what do I want to do? I'm going to do my parachute deployment. So that, we discussed that we need to change the effective area. So we need it's sort of like a switch. So let's have a look under switches, because we want to switch between two values. I think it was it switch case? No. What was it called? Let me have a look. In this case, I can't remember the name of it, so I'm going to look under the library browser. Signal routing. It's not a manual switch. It was a switch like this. Okay, they just call it a switch. So I drag that in. Did I drag anything in? Nope. Drag that in. So in this case, what I'm going to do, this is going to feed into my, in place of A, oops, don't want to get rid of it completely, sorry. Just delete that one. Okay, and I'm going to feed in the output of my logical block. So this block here is basically telling me, should I deploy my parachute? So that will be true, or it will be logical true when I do want to deploy my parachute, and logical false when I don't want to. So if my deployment is greater than 0, I want to use the big area, or if it's less than 0, I want to use the, or if it's false, I want to use my regular area. So this area down here is my non-deployed parachute area, and I'm going to use this one up here as my deployed parachute area. Okay, and this, instead of like pi times 4 centimeters squared for like a circular rocket, I'm going to use a big, like half meter radius parachute or something like that. Pi times 0.5 squared. So a meter diameter parachute packed into that rocket that's now deployed for my cross-sectional area. So I feed that in like so, and then the output of this goes back into where the area was feeding into my drag force before. So if the parachute's not deployed, I'm just a regular rocket, I've got a small cross-sectional area, or if my parachute is deployed, now I've got this big parachute area, which deploys based on this logic. Is my rocket going downwards, and am I within 15 meters of the ground? That's when my parachute will deploy. Okay, let's see if we've done anything useful. So get my scope up and run my simulation. Sweet. So early stages of the rocket haven't been changed there. So our thruster burns, it goes upwards, reach a maximum height of 60. We're falling, and all of a sudden something's happening around here. What's happening here? Well, hopefully it's 15 meters above the ground, and yes, my velocity is negative, so that the blue one is negative. And all of a sudden I deploy that parachute, I fluff it out, and now I've got a big drag force on it. So that's why my acceleration has suddenly jumped up with that big jolt. You know, your parachute deploys, you jolt, and that's that jump in acceleration. And quickly, that drag force is sort of slowing that rocket down. Look what happens to the velocity. It goes from a high negative value to a lower negative value, and now it's taking so much longer to get down to the ground. Here's our position, you know, falling very slowly. You know, it's now got a, instead of its terminal velocity before, it's now terminal velocity is like, you know, about 1.8 minus 1.8 meters per second there with that big parachute deployed. So yeah, that may or may not be realistic or useful, but it's a nice little show, and there's the peak of that force there. So realistically, this force wouldn't jump up with such a big discontinuity because a parachute doesn't deploy in infinite time, infinitesimal time. It slowly expands and the drag force gets applied. You know, it's a bit more of a smoother change, but that's the idea with that. So we've gone from a very simple system with just a rocket moving in one direction to something that's a little bit more complicated, right? With all these interconnections. So I don't know whether it's laid out okay or not. It seems okay. Let's just do a quick auto arrange and see if it does anything for me. Not too complicated for it. So you might spend some time going through and I guess you know, changing where these wires go in terms of the layout and stuff, but the core of it's there. You can read the constants like M and like A in from the workspace just by defining them in your workspace and then accessing them from the in variables. So like if I was to type in the forces and stuff like that, I can just reference, instead of 9.8, it would just be a reference G, which is a MATLAB workspace variable, and so on. Constants can be useful in terms of you see exactly what you're dealing with, but yeah, the working from the workspace, if you've got a lot of different what's the word I'm looking for? I've completely forgotten my train of thought. I just trailed off there. It'll come back to me if it's useful. So yeah, hopefully that's a few different blocks that you haven't seen before, or maybe a different sort of use for them. Let me know if there's any questions. Jeff, I've just seen your text chat from a while ago now. If there's anything you need me to clear up post it again, and I'll try and answer the question if you're still there. But yeah, sweet. The only other thing that we might want to do is maybe formalize some of this as a subsystem, right? Because all of this is starting to look a little bit complicated. So we will spend a little bit of time clearing it up, because if you submitted this as an assignment or something, you might even lose some marks for it looking pretty ugly. So one of the easiest things to do is add some just areas around things to help, I guess, delineate different areas and stuff. So off to the side, there's this area block. You can click and drag around a set of things. So we might highlight, all of this stuff to be, to sort of say, this is where all my drag forces are, right? And then you can move, I think, you can move that block around like that. And then, yeah, if you're doing your, forces to gravity and things like that, yeah, distinct inputs and outputs, exactly. The subsystem thing, so let's think we're working on a product, right, and we've gone, oh, okay, this is actually something that we might want to do. We might want to formalize this parachute deployment system as a subsystem. So if you highlight those blocks and right click on them, and you go create subsystem from selection. And what that does is shrinks all that input stuff down inside that subsystem. And so that thing had 2 inputs to it and 1 output. The subsystem might be called parachute deployment. We can double click on that, and we can actually have a look inside that subsystem now and see what's going on. And that's got our complicated logic in it. But really, from the outside, this is all we're interested in. We feed in the velocity, feed in the position, and it's the subsystem's job to tell us when do we deploy that parachute. So maybe we should have included something like this, this part of it as well, or even the whole drag force thing can be a little bit complicated. So, but that's the idea of a subsystem, just highlighting certain sections and creating it as a subsystem. It abstracts away some of the more complicated logic, and then you can go into those subsystems and see, and hopefully in the model browser, you can start to see your sort of big systems start to get broken down into subsystems, which is very handy a lot of the time. Haven't used them too much in my experience with courses, but yeah, certainly for large systems, if you jump on to the MATLAB and Simulink sort of communal area where you can upload stuff, or even downloading examples, you can get really, really big, complicated systems that will have plenty of subsystems in there. But that's the idea of this rocket, using the drag force and using the position to, I guess, create the drag force that acts and governs the dynamics of our rocket, which can be, yeah, you wouldn't want to solve this system by hand, basically. Definitely Simulink's the way to go for that. All right, so in the last 20 minutes, we're just going to practice forming differential equations into block diagram systems. And this is the starting point for a lot of the stuff you'll come across in your courses, is starting from a differential equation like this and just building it into a Simulink model. And we'll quickly build some of these. Don't want to spend too much time, so I might choose the more interesting ones. If you're familiar with second order differential equations, these two are actually entirely equivalent. They're both examples of damped second order systems. You'll find the block diagrams look exactly the same. So we might choose one of them. We might choose the Rlc circuit one. Get a bit of electronics coming into it rather than dynamics, but yeah, we'll choose some Rlc circuit. Then we might do the Lotka-Volterra population, which is a coupled dynamical system. And yeah, if we have time, we'll quickly do a transfer function one. But yeah, pretty simple once you get the idea of that, if you've done MATLAB transfer functions first. Okay, so let's do an Rlc circuit. Just create a new blank model. Yep, save my rocket. Save this one as Rlc. Okay, so constants, what I'm going to do with this one, I will define my constants in my MATLAB workspace. So R equals, let's say 1K resistor, let's go 10K E3, so 10K resistor. Let's go maybe a 1 milli inductor. And capacitor, something interesting. Let's go 10 micro. So R, L, and C are now defined in my base MATLAB workspace. So when I build my Simulink model, I can access those directly. Okay. Rlc circuit where V in equals LC times the second derivative of V out times RC dV out plus V out. Okay, so input is V in, so that's going to sort of happen on the left-hand side, and output is V out. We're going to be working across to the right-hand side. So how do we start these, right? This can be a little bit tricky, but the idea is to, or at least what I do, there may be another way, but typically what I do is you isolate the highest level derivative is the first thing that we do. So equivalently, this would be V in minus V out minus RC dV out. All of that divided by LC is then going to equal dV out, the second derivative of dV out. So once we've isolated that, things become a little bit clearer, because then we can start integrating upwards. So first thing I'll do is second order system. So I'm going to add in 2 integrator blocks. I'm just going to use 2 single ones. You could equivalently use a single second order integrator like we did in the last example, but I'm going to use 2 single order integrators. So the signal that comes in here is going to be my second derivative. It's going to get integrated up into my first derivative, and then we're going to integrate that signal up again into my my sort of base level highest, my V out signal. So second derivative is going to come in here, first derivative is going to be this signal here, and I just feed that straight in, and then out here is going to be V out. So now I'm going to need a scope. I'm going to want to look at that like that. This is going to be, the output of that will be V out. The output of this one is going to be dV out. And then the input to that one is going to be my, my second order derivative. And then V in, it could be anything really, but let's start with something like a step function. Pretty common. Step function, yeah, let's keep it a unit step function. And let's call that V in. Okay, so V in. Okay, so how does V in relate to the second order derivative, and what is the second order derivative? So second order derivative, we said, is going to be everything we're going to scale it by 1 on LC. So I know I'm going to need a gain here, and my gain value is going to be 1 divided by L times C, like that, and L and C being defined in my MATLAB workspace. If I hadn't defined those, let's say I messed up and call it M or something like that, I'll just show you what happens. Okay, the block highlights red because there's an unrecognized variable in that. So that will tell you if you're going wrong. But because I've got L and C defined there like that, it's all good. So if I divide everything or multiply it by 1 on LC, that's dividing, that's going to be my second order derivative because I need to scale by that. And then what's going into that? I've got going to need a summing block. Like that. It's going to have V in, there's going to be a derivative, and there's going to be a V out as well. So I need 3 different sums, and one of them is going to be a minus. Okay, so then I get V in, and then I need to take away, sorry, 2 of these are going to be a minus, my mistake. So hopefully it's clear that if I'm not doing this on paper, usually you'd work through this on paper first so you can see a little bit clearer exactly what I'm doing. But I'm rearranging this equation so that I get the second order derivative equals and then something on the right hand side. And then what's going on here is I'm formulating that right hand side of the equation. So V in, I need to minus RC times the first derivative of V out. So for the RC, I need another gain block. Just write gain is going to be R times C. Just rotate that around because it's going to come back this way. And I need the first derivative signal, so that comes from this point here. Okay, and then I drop that in there, so minus that, and then I'm also going to have a minus V out as well, and that's grabbed from this signal here. And I don't need to multiply that by anything, so I just drop that in like that. Join that up to that, and then we get the differential equation. So we isolated this, and this is all the things that are happening on the other side, scaling it down, and then we're integrating up to get all of our other signals and just grabbing them and scaling them as we need to. So if I run that and have a look, I get my step function for that particular system there. So the default step time for V in was step time is 1 there, so that's, you can see that turning on at t equals 1. Now, not particularly nice, so we might want to see if we can force some sort of underdamped behavior or something like that. So we could jump back into this one here, and we could reduce the damping. You know, that might be 1K instead of 10K, and we'll see what that does. Run it. We just reduced our times constant. Let's see if we can force something interesting. Let's make it a nice big 1 Henry inductor and see what happens. Nope, still pretty boring. Anyway, you get the idea. You can play around with those values and come up with a nice system that does something. Okay, so let's see if that did anything. Yeah, not really, just a bigger time constant, so you get the idea. Just modify those parameters as you need to for what system you're trying to solve. All right, and we'll quickly do this coupled Lotka-Volterra equation as well. So we're starting with this description of the dynamical system. Clear everything out. This one's a coupled system, so we'll see. You see we've got 2 different variables, x and y, and then 4 constant parameters, alpha, beta, delta, and gamma. So we'll quickly just define those. Let's just call them A, B, C, and D. Alpha equals 0.5, B equals 1, C equals 0.1. I'm just making these up. They could or may not be interesting. And D equals, let's make that 0.8, because why not? And then just quickly create a new model. Call it LV for Lotka-Volterra. Okay. So looking at our dynamical system, the derivative of x equals alpha times x minus beta times xy. So let's start with that. Might drop in an area up the top. This is going to be our x system. Okay, so we need at least one integrator. Oops, don't give me a second order one. Like that. So derivative of x is going to come into the left-hand side. That is equal to alpha times the out. So the output of this is going to be x. And then the derivative is equal to alpha times x. So I know I need a gain in here. Gain is going to be a for alpha that I defined in my workspace variable. Then I need alpha times x minus beta times xy. So I know I'm going to need a sum here. Yep. I need 1 plus and 1 minus. So alpha x, that one's going to drop into the plus. This one is going to be wrap around to that. So there's my alpha times the value of x minus, I know I need a, what do we got? Beta times xy. I'm going to need a product. So that is going to feed into that, and then I know my sum is going to be integrated up, and then beta x and y. So I can just have maybe 3 inputs for that, a constant block. Constant value is going to be b for beta. So beta is going to be first multiplier, second one is going to be x, which is this one here, and then y it's going to come from down here in a second. But because my x and y are so similar, I'm just going to quickly copy this whole area, paste that in, and it didn't copy all my blocks. See if I can get all that selected. Yep, copy paste. And now down here, I'm going to have my y system, which is just going to be a slightly modified version. And why has it gotten rid of, forgive me for a second, see if I can get this working a little bit better. Copy, paste, that's better. This is y down here. Okay, so y, the derivative of y is equal to, so I'm just going to modify this. I'm going to change this to minus and plus, so I don't need to modify too much. So minus, instead of that, it's going to be a gamma, except I called that one D because I didn't think ahead. So our A, B, C, and D. Gamma delta, maybe I'll call that C. Doesn't really matter. C, yep, my workspace variable, and then the plus of that is going to be delta D multiplied by xy. So this is y down here. Now I just need to cross these over. So I need one of my x signals grabbed from here and feeding into this product down here. And I need one of my y signals, like this one here, so this is y here, feeding into the product up here. So you can see how those two systems are coupled together by the values of x and y and the nature of this system of equations here. So that should be the Lotka-Volterra population. Scope. Let's feed in an x from here, and a y from here. And we'll see how I went with the choosing of these parameters, whether we get something interesting or not. You can have a look at the Lotka-Volterra stuff to see if the choose the best values. Now, why don't we get something interesting coming up? Because I haven't defined initial conditions, which is basically initial population in this case, but the initial condition might be 10. Let's start with 10 of each and see what happens. We start at 0 of each of predators and prey. Nothing much happens, so start with 10 of each of those. And there's our population here for X's and Y's, which should be named something a little bit better. So integrator, not great. So this is going to be X for him and Y for him. Okay, and we can see what's happening. X's and Y's like this. So obviously, the predators, if these were predators, the blues and the yellows were preys. So with these particular values, our predators, they thrive in the first instance because there's plenty of food for them with these constants. There's plenty of food, they grow in population. These ones are getting eaten real quick. They quickly drop to 0, but what happens? All of a sudden the predators have no food and they start dying off and will eventually reach 0 population. So that's what's happening in this one. You can get some quite interesting dynamics happening depending on the values of alpha, beta, gamma, and delta. But the ones that I've chosen give rise to that particular dynamics. I think that's probably just about it. You can try these other ones. You can try a transfer function one. You need to just be defining the numerator and the denominator in the way that MATLAB defines polynomial coefficients. And yeah, you just drop those in. Just remember, Simulink is a time domain solver. Even though this is a frequency domain thing, or Laplace domain, it's just still using dynamic and time domain techniques to solve that. Does it in a very smart way, but yeah, the time domain signal will go into a transfer function block and a time domain signal will come out of the other side of a transfer function block, which is what we'd use for this one, the transfer function. All right, so most of how I've come across it is modeling up differential equations, so definitely practice those. You'll use it a lot. Signals and systems, control systems, pretty much, yeah, dynamic differential equations, and you get to be able to do them relatively quickly if you solve for that lowest level derivative and then just feed in the different things coming into that. So definitely, I would recommend checking out some of the other models that are out there that other people have made. They can be very, very complicated ones. So there's all stuff on, yeah, like car control systems, like antennas and all this fun stuff that can get very complicated. But if they've done their job correctly, they've sort of abstracted away those really complicated logic as subsystems, and all you need to do is just feed it the things that are of use. So check those out and yeah, just focus on one section at a time, join them together, lay out your models nicely, name your things nicely, and you'll stay out of trouble. All right, that's the end of it. So thanks so much for coming along. I'll hang around for a bit for any other questions. But if there's anything else, happy simulinking. Thanks so much. No trouble. Thanks so much. I'll catch you all next week for Advanced MATLAB, which I'm still writing, but I'll get there. Should be fun. Yeah, should be good. All right. Signing off now, guys. I'll catch you later.